Currently, most conventional nuclear reactors make use of uranium to produce energy. It makes use of the uranium-235 reaction, which is as rare as platinum and silver. Since it is using uranium, you will require water cooling, and it uses solid fuel. It requires a continuous supply of materials to kickstart the energy. To form uranium. Thorium-based nuclear reactors make use of the reaction of thorium-232 to form uranium-233, and in this process it generates energy. Thorium is much more abundant than uranium on Earth and is mostly fertile. It produces less radioactive waste than other reactors since the reaction can be fully utilized to generate energy.
It's not based on water cooling, and it doesn't use solid fuel. It's based on fluoride salts as a nuclear fuel. You have to heat them up to about 400 degrees Celsius to get them to melt, but that's actually perfect for trying to generate power in a nuclear reactor. Here's the real magic. They don't have to operate at high pressure. They don't have to use water for coolant, and there's nothing in the reactor that's going to make a big change in density. Unlike the solid fuels that can melt down if you stop cooling them, these liquid fluoride fuels are already melted. In normal operation, you have a little piece of frozen salt that you've kept frozen by blowing cool gas over the outside of the pipe. If there's an emergency and you lose all the power to your nuclear power plant, the little blower stops blowing, the frozen plug of salt melts, and the liquid fluoride fuel inside the reactor drains out of the vessel, through the line, and into another tank called a drain tank. Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. We could use thorium about 200 times more efficiently than we're using uranium now. Because the lifter is capable of almost completely releasing the energy in thorium, this reduces the waste generated over uranium by factors of hundreds and by factors of millions over fossil fuels. In 2007, we used 5 billion tons of coal, 31 billion barrels of oil, and 5 trillion cubic meters of natural gas, along with 65,000 tons of uranium to produce the world's energy.
So I have a friend who's trying to start a rare earth mine in Missouri. Jim, how much thorium do you think you'll be pulling up a year? He goes, I think about 5,000 tons. 5,000 tons of thorium would supply the planet with all of its energy for a year. And he goes, and there's like a zillion other places on Earth that are just like my mine. It's a nice mine, but it's not unique.
These are the various types of thorium reactors. They are heavy water reactor, high temperature gas-cooled reactor, boiling or pressurized water reactors, fast neutron reactors, molten-salt reactors, aqueous homogeneous reactors, and accelerator-driven reactors. Heavy water reactors are well suited for thorium fuels due to the combination of excellent neutron economy, slightly faster average neutron energy, which favors conversion to uranium-233, and flexible online refueling capability. Furthermore, heavy water reactors are well established and widely deployed commercial technology for which there is extensive licensing experience. These are well suited for thorium-based fuels in the form of thorium mixed with plutonium or enriched uranium, coated with pyrolytic carbon and silicon carbonate layers which retain fission gases. The fuel particles are embedded in a graphite matrix that is very stable at high temperatures. Such fuels can be irradiated for very long periods and thus deeply burn their original fissile charge. Boiling water reactors. Fuel assemblies can be flexibly designed in terms of rod with varying compositions and structural features, and enabling the fuel to experience more or less moderation. This design flexibility is very good for being able to come up with suitable heterogeneous arrangements and create well-optimized thorium fuels. Viable thorium fuels can be designed for a pressurized water reactor. Even though pressurized water reactors are not the perfect reactor in which to use thorium, they are the industry workhorse, and there's a lot of pressurized water reactor licensing experience. In fast neutron reactors, thorium can serve as a fuel component for reactors operating with a fast neutron spectrum, in which a wider range of heavy nuclides are fissionable and may potentially drive a thorium fuel. There is, however, no relative advantages in using thorium as a fertile fuel matrix in these reactor systems. Molten-salt reactors are still at the design stage, but are likely to be very well suited for using thorium as a fuel. The unique fluid fuel can incorporate thorium and uranium fluorides as part of a salt mixture that melts in the range of 400 to 700 degrees Celsius. This liquid serves as both heat transfer fluid and a matrix for the fissioning fuel. The fuel circulates through a core region and then through a chemical processing circuit that removes various fission products and the valuable U-233. The subcritical accelerator-driven reactor system is an unconventional nuclear fission energy concept that is potentially thorium-capable. Neutrons are produced when high-energy protons from an accelerator strike a heavy target like lead. These neutrons are directed at a region containing a thorium fuel, which reacts to produce heat, as in a conventional reactor. The system remains subcritical.